Blue skies. Calm every pilot's nerves. So why do nearly 9 out of 10 general aviation accidents happen when the weather is perfect? It is a paradox grounded in hard numbers. The latest AOPA Nall Report shows that fair weather breeds risk, not safety. Pilots relax, traffic explodes, and the real threats become invisible. What is it about clear days that makes them statistically deadlier than thunderstorms? And how does human biology set the ultimate trap? The answer starts with the data and a rethinking of everything you thought you knew about safe flying. A glance at the AOPA Nall Report upends the most common belief in aviation safety. The numbers are not subtle. In the most recent edition, nearly 75% of all general aviation accidents occurred in visual meteorological conditions, what most pilots call a blue sky day. That means 3 out of every 4 mishaps happen when the weather is clear, visibility is good, and wind is light. Only a small fraction, less than 15%, happen in instrument meteorological conditions, the kind of weather that keeps most pilots grounded or demands strict adherence to instrument procedures. This pattern has held steady for years. The 2023 Nall Report, analyzing 1,097 total accidents, found that 929 involved non-commercial fixed-wing aircraft, and about 88% of these took place in visual meteorological conditions. Fatal accidents follow a similar trend. About 3/4 of deadly crashes occurred in clear weather. The tables in the report show this year after year, with only minor fluctuations. Even when normalized for flight hours, since more people fly when skies are clear, the dominance of visual meteorological conditions accidents remains. Night flights tell the same story. 84% of night accidents happened in visual meteorological conditions, compared to just 14% in instrument meteorological conditions. The difference is not just statistical noise. It is a persistent trend visible in every phase of flight and every major accident category. Loss of control, fuel exhaustion, mid-air collisions, each one is overwhelmingly a clear weather event. The data does not blame the weather. It points to something deeper in pilot behavior. The Nall Report tables and charts make it plain. Blue skies do not guarantee safety. Instead, they create the backdrop for most general aviation accidents in the United States. The numbers demand a closer look at why comfort, not chaos, so often precedes disaster. Clear skies draw pilots out in droves. On a sunny weekend, the airspace over popular airports swells with dozens of aircraft, student pilots, seasoned flyers, and families heading out for a day trip. The same weather that fills runways with takeoffs and landings also fills the sky with converging flight paths. Traffic density. In general aviation, spikes sharply in good weather, transforming what feels like open air into an invisible maze of potential conflicts. Mid-air collisions almost never happen in storms or low visibility. In poor weather, air traffic controllers keep aircraft separated by altitude and route, and many pilots stay on the ground. But when the weather is perfect, the skies belong to everyone. Pilots fly direct, cut corners, and sometimes skip radio calls at uncontrolled fields. The result is a clustering effect, multiple planes approaching the same point at the same time, each trusting their eyes to spot traffic that may be hidden in the glare or lost in the blue. The AOPA Nall Report confirms this pattern. Nearly all mid-air collisions occur in visual meteorological conditions, with the overwhelming majority happening within 5 miles of an airport, often during climb or approach. On a clear day, the risk of a mid-air collision is not spread evenly. It concentrates around busy corridors and non-towered airports, where see and avoid is the only defense. Risk compensation plays a silent role. When the sky looks safe, pilots relax their guard. They may fly closer to other aircraft, assume others will see and avoid, or rely on habit rather than vigilance. This complacency invites shortcuts and assumptions, multiplying the hazard in ways that are hard to see until it is too late. The crowded sky is not just a matter of numbers, it is a behavioral shift, where safety margins shrink as confidence grows. This convergence of traffic and complacency sets the stage for the next threat. It is not just that there are more planes, it is that our own biology makes it harder to see them. In the cockpit, the human eye faces a challenge it was never designed to solve. In a world with no edges, no clouds, and no visible horizon, your vision defaults to a resting state. FAA researchers call this phenomenon empty field myopia. When the sky is a uniform blue, the eye loses its anchor. Instead of focusing at infinity, where distant traffic or terrain might appear, your lens relaxes to a point just inside the cockpit, typically around 6 feet ahead. This is not a defect or a matter of needing glasses. Even pilots with perfect 20/20 vision experience it. Accommodation studies at the FAA Civil Aerospace Medical Institute demonstrated this effect in both simulators and real aircraft. When test subjects were asked to search for distant objects in a featureless sky, their eyes repeatedly settled on the windshield itself. Targets beyond the glass, other aircraft, radio towers, even large clouds became harder to spot, not because they were invisible, but because the eye was not tuned to the right distance. The implications are subtle but serious. In a busy sky, a pilot may scan left and right, believing every inch of airspace is under watch. But if the eye is not actively reset by focusing on a distant cloud or the horizon, entire aircraft can pass unnoticed. The blue sky, instead of being a clear window to the world, becomes a kind of optical trap. The biology of vision, left to its own devices, quietly undermines the most fundamental tool in collision avoidance: seeing what is really out there. Every scan of the sky is interrupted by a rapid, involuntary movement called a saccade. Rather than gliding smoothly, the eye jumps from point to point, pausing only briefly to gather detail. During each saccade, which can last from 20 to 200 milliseconds, the brain suppresses incoming visual information. This phenomenon, known as saccadic masking, creates a series of micro-blind spots, moments when the outside world is effectively invisible, even though the eyes remain open and moving. In the cockpit, these intervals add up. Eye-tracking studies from the FAA Civil Aerospace Medical Institute show that when a pilot scans the windshield, the cumulative blind time can reach 10 to 20% of the total scan. That means for every minute spent searching for traffic, 6 to 12 seconds are lost to these invisible gaps. An aircraft crossing the field of view at cruise speed can travel hundreds of feet in that time, enough to slip through undetected if it happens to pass during a saccade. The danger is not just theoretical. Saccadic suppression is a universal feature of human vision. It cannot be trained away or eliminated by practice. Even the most disciplined pilot, scanning methodically, is subject to these blind intervals. The only defense is awareness, understanding that the act of looking does not guarantee seeing, and that the brain's natural editing process can erase threats from perception without a trace. In a crowded sky, these invisible gaps in vision become the silent accomplice to every close call. Collision courses in aviation defy intuition. Two airplanes, each cruising at 120 knots, close the distance between them at a combined speed of 240 knots, roughly 4 nautical miles every minute. When these aircraft are aimed directly at each other, the geometry of their paths creates a hidden threat called constant bearing, decreasing range CBDR. In this scenario, the other plane does not drift across your windshield. It does not grow or shrink, and it does not veer left or right. Instead, it remains a fixed point in your line of sight, motionless against the blue sky. Your peripheral vision, tuned by evolution to detect movement, fails to register the danger. The numbers reveal just how unforgiving this situation can be. At a separation of 1 nautical mile, closure at 240 knots leaves 15 seconds before impact. For most of that time, the opposing aircraft appears as a tiny dot, smaller than a bug splattered on glass. At half a nautical mile, the window narrows to 7 or 8 seconds, yet the target is still little more than a speck. Only in the final moments does the image blossom, expanding rapidly from pinprick to full silhouette. By then, the time available for recognition and evasive action has nearly vanished. This is not a rare or theoretical problem. NTSB investigations into mid-air collisions repeatedly cite CBDR as the underlying cause. The physics do not care about pilot experience or clear skies. If two aircraft are on converging paths and neither alters course, the illusion of safety persists until the last possible instant. The countdown from 1 nautical mile to impact happens in silence, masked by the very stillness that makes the sky seem so inviting. The mathematics of closure offer no margin for hesitation. In these moments, the difference between a near miss and a catastrophe is measured in seconds, and in the ability to spot a threat of bouffage that refuses to announce itself. On October 23, 2014, 2 aircraft converged in the clear autumn sky over Frederick, Maryland. The Cirrus SR-22, a high-performance single-engine plane, and a Robinson R-44 helicopter were both operating under visual flight rules. Weather was not a factor. Visibility stretched for miles, the air was calm, and the sun lit every detail of the landscape below. Yet within seconds, both aircraft were reduced to wreckage. The NTSB reconstruction of ERA 15FA025 reveals how the invisible geometry of collision unfolded. The Cirrus had departed from the Frederick Airport minutes earlier, climbing to 1,500 feet. The R-44 was returning from a local training flight, entering the pattern on a standard approach. Both pilots were communicating on the advisory frequency, but neither reported seeing the other. Radar data showed their paths intersecting almost precisely over the airport boundary. For nearly a minute, the 2 aircraft closed the gap at a combined speed exceeding 160 knots. From the cockpit, the oncoming aircraft would have appeared as a stationary dot, constant bearing, decreasing range, never drifting left or right, never growing in size until the final moments. Eyewitnesses described the impact as sudden and violent. There was no sign of evasive action, no abrupt turns or dives. The NTSB investigation found no mechanical faults, no radio failures, and no weather complications. The probable cause cited the failure of both crews to see and avoid each other, a phrase that in this context conceals the deeper reality of human limitations. The report highlighted that both aircraft were operating in perfect weather, with unobstructed views in all directions, yet the collision was invisible until it was unavoidable. An NTSB investigator, reviewing the radar and audio tapes, explained that this was the textbook case of constant bearing, decreasing range. The pilots had no visual cues, no motion, no looming threat until the final seconds. By the time the aircraft blossomed in the window, there was no time left to react. The Frederick case is not an outlier. It is the consequence of physics and biology colliding in open air. The illusion of safety created by a flawless sky can erase the warning signs that pilots trust. When the invisible threat remains motionless, the best intentions and sharpest eyes may not be enough. Fuel exhaustion in general aviation rarely makes headlines, yet the NTSB files are filled with cases where clear skies and confidence proved fatal. In the docket ERA 19FA107, a Cessna 172 pilot departed Lakeland, Florida on a routine visual flight rules trip. The weather was flawless, unlimited visibility, calm winds, a bright sun overhead. The pilot, with over 1,200 flight hours, pressed on as the low fuel warning illuminated. Instead of diverting, he circled his intended destination for nearly 20 minutes, convinced he could stretch the remaining fuel. The engine quit at 1,200 feet above the ground. The forced landing ended in a wooded field, destroying the aircraft and leaving the pilot seriously injured. The NTSB's probable cause read, "The pilot's failure to properly manage the available fuel quantity, which resulted in fuel exhaustion and a total loss of engine power during cruise flight." The report noted the pilot's choice to continue after low fuel alerts, despite clear opportunities to land safely. A similar pattern appears when pilots fly visually into instrument meteorological conditions. In one recent docket, a pilot launched into a day of scattered clouds and 10-mile visibility. As the flight progressed, deteriorating weather closed in. The pilot, flying visually, pressed onward into lowering ceilings and rain, rather than diverting or requesting assistance. Spatial disorientation set in, ending with a loss of control and a fatal crash. The NTSB cited the pilot's decision to continue visual flight into deteriorating weather conditions as the primary cause, with inadequate transition to instrument conditions as a contributing factor. These reports share a common thread: optimism in the face of perfect weather. The comfort of blue sky tempts pilots to gamble, to stretch fuel, to press on when caution would save lives. The data is clear. When the sky looks safest, discipline matters most. A disciplined scan is not just a recommendation. Discipline is the foundation of survival in clear skies. The Federal Aviation Administration Advisory. Circular number 90-48D lays out the method. Break the sky into 10 to 15-degree blocks. Focus on each segment for at least 1 to 2 seconds, then move your gaze to the next. This systematic approach, often demonstrated by experienced flight instructors, forces the eyes to reset and the brain to process each slice of airspace. Instead of letting vision drift, you actively search, moving your head and refocusing your eyes on distant objects. Never trust a passive glance. Fuel management demands the same rigor. Regulations require a 30-minute reserve for visual flight rules flights, but seasoned instructors teach a stricter rule. Always plan for at least 45 minutes beyond your destination and treat 1/3 of your usable fuel as untouchable. This margin is not a luxury. It is a shield against the optimism that creeps in on a blue sky day. Pilots who land safely are those who decide to divert early, not those who hope the numbers will work out. Technology, too, is a tool if used with intent. ADS-B traffic displays and flight following services are now widely available, giving pilots a second set of eyes, especially in busy airspace. But these aids work best when paired with active habits. Check the screen, verify with your own scan, and never assume the system sees everything. The checklist for a safe flight in perfect weather is simple but strict. Scan methodically, manage fuel conservatively, and use every tool available. What looks effortless from the ground is, in reality, the product of relentless discipline and practiced paranoia. Every year, the AOPA Nall Report confirms it. Clear skies breed the most risk, not storms, but comfort. In today's crowded airspace, biology and psychology do not change, even as technology advances. The real threat is not what you see, but what your brain convinces you to ignore. Vigilance is a choice, one that saves lives. Fly today like safety depends on it, because it still does. Share your thoughts below.